Now, today we will be talking about diuretics. First of all, we have to define what is a diuretic, right? And especially there are two terms which are sometimes used interchangeably. There is a term called natriuresis, diuretic, natriuretic, and there is a term which is called diuretic. Many people use them interchangeably, but literally they mean a little difference. Who will tell me what is natriuretic agent? What is meant by an agent which is natriuretic? Yes, please. Right, very good. Any substance or any drug or any agent, when it introduced in your body or in biological system, it increases the output of urinary sodium. Right? It causes increased loss of sodium in urine. So any agent which increases the loss of sodium in urine, it is called natriuretic agent. But when we strictly define diuretic agent means any agent which increases urine output. So it means anything which increases the sodium output in the urine, that should be considered natriuretic agent. And anything which increases the urine volume, that is called diuretic agent. Now, most of the drugs which are used, which actually are natriuretic, when they produce some degree of natriuresis, it means there is increased loss of sodium in the urine. This extra loss of sodium pulls extra water with it into urine. So it means natriuretic drugs are diuretic as well. It means natriuretic drugs are diuretic as well. Right? Now, let's go into detail that what is the normal urine output, what is normal renal blood flow, and how nephron works, right? First of all, we'll talk about, let's suppose here is your cardiovascular system or circulatory system, right? Now you know circulatory system is supplying the blood through arterial tree to the all body and every organ, including your kidneys. You know kidney is made of a lot of specialized tubes which are called nephrons. How many nephrons you have in one kidney? You never counted it, too busy in your life. How many nephrons you have in one kidney? About 1.2 million. He has been counting it. He is right. So, in two kidneys, you are having about 2.4 million nephrons. What I really mean that you are a millionaire as far as nephrons are concerned. An average adult person has somewhere between 2 to 2 million nephrons. What are nephrons? These are very specialized tubular structures, epithelial tubes present in the kidneys which are concerned with urine formation. Right? And of course, when anything which increases the urine output or which increases the sodium output, that must be working on nephron. It means natriuretic agents or diuretic agent alter the function of the nephron in such a way that there is increased sodium losses in the urine or there is increased water loss or volume in the urine. So first of all, we must see how a normal nephron works. Right? First we'll talk about how a normal nephron works, what is the normal volumes of urine produced, how normally sodium is handled by different segments of the nephron, and then we'll talk about how different drugs alter the function in different segments of the nephron producing natriuresis or diuresis. Okay, we start with a very fundamental concept that let's suppose this is your cardiovascular system and out of your kidney I bring one nephron here. Out of the millions of the nephron, I bring one nephron here. Every nephron has one filtration unit, right? And to this filtration unit, blood flow is coming, right? Now this blood flow, this is glomerular capillary tuft and this is Bowman's capsule. Together they make the glomerulus. And basically what is glomerulus? This is a area into which blood come into kidney, right? And it is having on the other side Bowman's capsule, the very earliest part of the nephron, and it acts as a filtration unit. Now what really happens when blood is coming to this area, some part of the plasma, some components of the plasma are basically filtered into nephron, right? Now from here, what happens? There are different parts of the nephron. This earliest part of the nephron is called proximal convoluted tubule. Of course, it is made of different type of cells, right? This is epithelial tube made of epithelial cells. Here is loop of Henle. This is the descending part of loop of Henle. This is the ascending part of loop of Henle. This is the hairpin turn. Of course, this is in near cortical area, and this is in the medullary area. And again, this is also made of, what are these things? Epithelial cells, right? Now, what really happens that in this area, it becomes wide, and we call it thick part of ascending limb of loop of Henle, this part. And of course, it is also made of different type of cells, right? As you know, all the nephron is made of an epithelial tube. Is that right? These are all epithelial cells. Now we have drawn some parts of the nephron. What we are seeing that when the fluid is filtered from here, first it appears into Bowman capsule. From there it passes through the proximal convoluted tubule. Then it goes through descending limb of loop of Henle. Through the hairpin turn, the fluid moves again towards the cortex, and initially there is, what is there? Thin part of ascending limb of loop of Henle. Then there's thick part of ascending limb of loop of Henle, right? From here, then what really happens? This is, yeah, what is it? This is distal convoluted tubule, and eventually this distal convoluted tubule will end up into, yes, collecting duct. Of course, again, it is also made of cells. Now there are a few important things which we have to understand, that what are the basic functions of nephron. As we know, first of all, it should have a filtration unit. Fluid should move into Bowman capsule. Now fluid will be moving through this tube, and eventually a part of the fluid reaches up to the end of the tube, and that part of the fluid which appears at the end of the tube, this is called urine. This is called urine. What is urine? Urine is the fluid which appears at the end of the tubule. Now, one thing which we have to learn is that what is the amount of blood flow per minute to the kidney. Now let's relate a very basic concept. What is the amount of blood flow to the kidney? Out of that blood which is coming to kidney every minute, how much is the plasma? Out of the plasma, how much fluid is filtered? Out of that filtered amount of the fluid, a filtered volume of the fluid, how much is really going back to the body? How much is further added to this area? And eventually, out of this total fluid, what really appears here? We'll talk about this thing. First of all, number one, the urine is formed in three processes. Process number one is, yes, filtration. Process number one is filtration. The fluid is filtered. Process number two is, on the way when fluid is going down, going along the nephron tube, a part of the fluid is reabsorbed and going back to the body. Is that right? But some of the fluid is actively, you can say some of the components, right, or some of the substances are actively secreted into tube, nephron tube. Now, so what we can say, all the fluid which really come into this tube is by through sources. All the substances which come to the lumen of this tube is through two sources. Main source is filtration, plus some substances are coming through secretion. So we can say that this tube is receiving the fluid mainly by filtration process and some substances from secretory process, right? So this total amount of filtered and secreted substances in the tube minus the substances which are reabsorbed, and what is left over, that is called urine. Now let's come to the let's calculate the things minute by minute. Right now, every minute, how much blood is going to your both kidneys, right? Again, it depends on your cardiac output. and so many other factors. In normal physiological situation, heart is producing how much cardiac output per minute? 5 liters per minute. Usually, in normal circumstances, your heart is pumping how much blood into arterial tree every minute? 5 liters. Out of this 5 liter, we say 20% goes to 20 to 25% goes to kidneys. It means whatever blood is being pumped out of the heart, about 20 to 25% is going to the kidney. Out of this 5 liter, if we make that 20% of the 5 liter, it should become how many liters? 1 liter per minute. So what did we learn right now? All of you know heart is pumping how much blood per minute to your arterial tree? 5 liter. Out of that, how much blood is going to your renal vasculature? 1 liter. That is 1 liter. So now we can say your kidneys are perfused approximately with 1 liter of blood every minute. When 1 liter of the blood is passing through it, all of the good students know that out of this 1 liter, there are cells and there is plasma. Right? Cells are about 40% and plasma is usually about 60%. So rather than total blood flow, if we talk about the plasma flow, so out of 1 liter of blood, how much plasma will be coming? Yes? How much plasma per minute will be passing through it? 60% of the blood. Right? You see, I have said it that out of 5 liter cardiac output, 1 liter is coming to renal system. Out of this 1 liter, 40% is cell, 60% is plasma. It means how many ml are cells? 400 ml are cells and 600 ml is plasma. So if I ask that through your all nephrons, if this nephron is representative of all your collective nephrons, right, how much blood is passing through this area entering to glomerulus, we say per minute is 1 liter. But out of that blood, how much is the plasma per minute? What is the plasma flow rate? That is 600 ml. So we can say that about 600 ml plasma is passing every minute through your renal glomeruli. Out of this, how much really filters out? Everything does not. Again, look, a part of it goes into Bowman capsule and rest of it moves forward. Is that right? Look here. This is afferent arteriole. Here it is efferent arteriole. And we can say afferent arteriole bring 1 liter blood every minute to glomeruli. Or we can say 60% of that blood, that is plasma, afferent arterioles bring 600 ml plasma flow every minute to your glomeruli. Out of that, some is filtered and other is going to the efferent arteriole, which will break down into pericapillary networks and other vasa recta. These are the capillaries which are around the nephron to reabsorb certain substances and secrete few. Now, if it is 600 ml entering into this every minute, how much is really filtered? Answer is approximately 20%. Answer is approximately 20%. Now 20 is very important here. Out of cardiac output, how much blood come to kidney? 20%. Out of plasma flow per minute through glomeruli, how much is really filtered? 20%. So if we say 600 ml is passing through it, if 10% is the filtration, of course this filtration usually is having very little proteins or practically no proteins, right? So it means protein and cells don't pass through it in a normal healthy kidney, not in any significant amount, especially proteins. So we can say the thing which is really filtered is water of the plasma with its soluble substances which have molecular weight less than albumin, right? Small solutes. Now again, I said how much will be filtered? 20%. Now, out of 600 ml, if 10% is filtered, it means every minute 60 ml is filtered. If I say every minute 20% is filtered, it means how much is filtered? 120 ml. So all of you must be knowing that every minute how much fluid is filtered. Yeah, every minute how much filtrate is appearing in Bowman capsule? 120 ml, 120 mLs. Is that right? Per minute. We also call it glomerular filtration rate, GFR. Now, what we have learned up to now, we have developed a relation between the cardiac output and renal blood flow, between the renal blood flow and the renal plasma flow, and glomerular plasma flow and filtration. Is that right? So if I asked you right now, normal person, what is the cardiac output per minute? 5 liter. Out of that, how much percentage goes to kidney? 20%. What is the 20% of 5 liter? 1 liter. So how much blood is going to your kidneys per minute? 1 liter. Out of that 1 liter, how much is plasma? 60%. So 1 liter is the blood flow through the kidney per minute. What is the plasma flow? 600 ml. So if we say 600 ml plasma is passing every minute through your glomeruli, 20% filter down and 80% goes to the peritubular capillaries and other capillary loops like visa recta. Now, so how much is really filtered? 120 ml. So a good doctor knows that on average, a normal person's kidney nephrons are receiving 120 ml of filtrate every minute. Is that clear? Normal person's glomeruli, or you can say Bowman capsules, right? They are receiving how much filtrate? 120 ml per minute. Now, out of this 120, look here. Now it is passing through the tube. This filtrate is passing through the tube. Lot of substances are reabsorbed back to the blood. Some substances are added by the secretory process. So, what really happens as fluid is passing along the nephron, as this filtrate fluid is passing along the tube, we call it tubular fluid. What is this? Tubular fluid. Here it is interstitial fluid, right? This is intracellular fluid. Here it is tubular fluid. What is this? Intracellular fluid. And what is it? Interstitial fluid. And what is it? Blood. Is that right? So there are 4 types of fluid right now here. That filtrate is passing through the tube as tubular fluid. What is tubular fluid? Right? Tubular fluid is filtrate plus secreted material. And on the way, when tubular fluid is moving, some substances are reabsorbed and some substances are added. It means the epithelial cells in the wall of the tube are processing the luminal fluid. They are processing the tubular fluid. And when they are processing the tubular fluid, on this process, as fluid is moving forward, composition of fluid keep on changing depending upon what are the substances which are pulled back to the body and what are the substances which have been added. And as fluid in the end appears, of course on the way the substances which we need in our body, they are pulled back, and substances which we really don't need, they are secreted there. Is that right? But anyway, this tubular fluid, as it is passing through different segments of the nephron, they are being processed. And as they are being processed, what really happens that they appear in the end as a drop of fluid, and this drop of fluid is called urine. Now my question is very, very simple. I'm saying that every minute, how much fluid is represented to your nephron? Approximately 120 ml. Right? Out of this 120 ml, some is reabsorbed and some is added. In the end, what really appears here is urine. Every minute, out of 120 ml, please attention, every minute, out of 120 ml, how much appear in a normal person as urine? Question goes to this young lady. Yes. Every minute, how much fluid appears as urine at the end of the nephron? I have told you what we have put in the beginning of the nephron is approximately 120, maybe few ml more will be secreted. So approximately we can say in whole your nephron system, every minute we put 120 ml. Is that right? In the end, urine appears. So we put 120 ml in a healthy person's, and what we get at the end after the whole processing of the fluid, how many ml fluid per minute?
Would be roughly the same.
It will be roughly the same, or will it be different? You have to be clever. Yes, madam is coming up with the answer. You just keep silent, all of you. Yes. How much fluid will be coming here per minute? It's a very fundamental question, isn't it? That a good student know. This is a tube. We put 120 ml here on the head of the nephron. From the tail of the nephron, every minute, how much fluid is coming out? Yes, please.
120 ml.
Okay, now let's see. For a while we just trust she is right. Of course, I will tell you why she is not right. But listen. She says a very dangerous statement. She says every minute 120 ml is coming as urine. Is that right? Now, let's calculate how much urine she will be passing per day. Look, every minute, in 1 hour, how many minutes are there?
60.
Okay, she knows good, confidently that every hour is 60 minutes. And in 1 day, how many hours? Yeah?
24.
24. And kidney work intermittently or continuously, healthy kidney? Yeah? Continuously. Now look at it. She has 60 minutes per hour and she has 24 hours to produce the urine. So how many minutes she has total? Of course, 60 into 24, it will become something like this. So, these are the number of minutes per day. Is that right? Now, according to her calculation, how much urine she is producing, let's look at the situation. She has 120 ml urine. She claims that every minute she is producing how much urine? 120 ml. So, 1 day, 1440. Now, let's see how much is the urine. Oh my God. Okay, yeah?
160 liters.
You have missed. How many liters? Okay, make it 100 so that we can make it easy. Attention please, let's make it easy. Okay, it's not 120 ml, it is 100 ml. 100 ml, so what it will be? 1440, if these are mLs per day. So per day, how much will be your liters of urine? About 144 liters per day. Oh my God, your own weight is not that much. It's a very dangerous statement she has passed. I don't know how she can produce more than 100 liters of urine per day.
I'll change the statement.
Okay, she will change the statement. Are you sure you don't produce that much urine? Okay, now you tell me what is your latest assessment of your urine out?
1 ml urine
Only 1 ml urine
per minute.
per minute. Okay, now you see this is called personality which only moves at the ends. About 10 minutes back she was saying every minute she is passing how much urine? She is making how much urine? 120 ml. Suddenly, I don't know, somehow she decided it's too much and now she end up with output per day. Every doctor must know that what is the normal urine output per day, right? Actually, it will be better, urine output keep on increasing and decreasing, right? We should say what is the abnormal urine output. If we define the abnormal urine output, then we can understand it between the two abnormal extremes. There must be normal urine output. The minimum urine output which a normal person should have is about 500 ml per day. This is the minimum. And maximum, you may have any amount, but still, we say when urine output is less than 500 ml, we say there is oliguria. Some people cut off at 400 ml. But anyway, what is oliguria? Oliguria is when your urine output in 24 hours is less than 400 or 500 ml. And polyuria is when your urine output is polyuria. Yes, polyuria means excessive amount of urine, right? That is more than 3500 ml per day. So again, anyone who produces urine less than half liter per day should be considered oliguric, and anyone who produces urine more than 3.5 liters per day, he should be considered polyuric. And it means anyone who is producing urine output somewhere in between should be considered normal. On average, normal person produces about 1.5 liters per day. 1.5 liter. Of course, this amount varies according to the environmental temperature and according to the input of the fluids and many other factors. But we can say, let's suppose an average person is producing 1.5 liter of urine per day. When we say that average person is producing approximately 1.5 liter urine per day, it means normal person is producing how much urine? 1500 ml per day. Now let's go to our previous calculation. In one day, how many minutes you have? You never counted it. Of course. In one day, how many minutes you have? 16 to 24 is 14? 40. And if hypothetically, if I say that you are producing 1 ml urine per minute, it means 1414 to 1 ml is equal to 1440 ml per day. So we can say that every minute, if we are getting 1 drop of 1 ml urine here at the end of the nephrons, then it means in 1440 minutes of per day, you are producing this much urine. And this is very much near to what we have guesstimated or estimated the volume. So what did we learn here? A very, very important thing. What we really learned here is that your nephrons are master processor. When they're processing the filtered and secreted substances and reabsorbing them, they're processing in a great way what they are doing. Out of 120 ml fluid which enters here into nephrons every minute, only 1 ml appears as urine. And somehow, when every minute 120 ml is passing along the tube of the nephron, all the things which are required by the body are pulled back. And only the waste materials are left behind, and some waste are also secreted. And eventually, out of processing of 120 ml of the filtered material every minute, this master chemist, make 1 ml urine. And during this process, it keeps your fluid balance, electrolyte balance, acid-base balance within normal range. This master processing machine, if there's more acid in the body, it will make the urine acidic. If there's more alkali in the body, it will make the urine alkaline. If there's excessive sodium in the body, it will bring more sodium out. If there's excessive potassium in the body and it's functioning normally, it will bring extra potassium out. If there's less sodium in the body, it will save the sodium in the body and bring less. So what I'm saying, nephrons are the master chemical processors. They chemically process all the filtered material, right? And out of 120 ml every minute, which they receive as filtered material, they end up with only 1 drop of urine every minute. This 1 drop is approximately how many ml? Just 1 ml. And in that 1 ml, whatever the waste product body has produced every minute, that is appearing. Is that clear? So in a very simple way, we can say, if for our convenience calculations, if we say there is a person who has approximately 100 ml filtrate, again it is also within normal range, healthy. If there is a person that every minute his nephrons are receiving how much fluid? 100 ml. Out of this 100 ml, when it is passing along the way, how much you receive here? Just 1 ml. It means how much is really taken back to the body? 99 ml. It means that on average, usually out of whatever glomerular filtrate is there, plus secreted material is there, 99% is reabsorbed, and approximately 1 ml is appearing as, or 1% of the fluid with the waste product is appearing into urine. Now listen carefully. If we give a drug which has the capability to convert 1 ml output per minute into 5 ml, it will be very powerful diuretic. Because urine output will be 5 times. From 1.5 liter it will go to 7.5 liter. And if there's a, so what I'm talking about, what diuretics have to do? Diuretics or natriuretic drugs have to play with nephrons and play only a little. Normally what nephrons are doing? Out of tubular fluid, 99% is reabsorbed, only 1% is appearing as urine. Right? And if along the nephron there are points which I will explain into detail, the different areas which are reabsorbing salt and water, sodium absorption or water absorption in different ways. And if drugs interfere with different segments of the nephron in such a way that sodium reabsorption or water reabsorption is reduced, there will be excessive output of urine, and we say that if sodium is becoming primarily excessive, we say this natriuresis. And as I told you that whenever sodium is appearing excessive there, it will bring along with it extra water, and if sodium is bringing extra water along with it, it means natriuresis is also, the substance which was natriuretic is also diuretic, right? So the next logical step in our lecture must be that we must understand. What should we understand? We must understand what are the normal mechanisms along the tube to reabsorb the sodium. For example, proximal convoluted tubule reabsorb the sodium in a different way. Thick limb of ascending part of loop of Henle reabsorb sodium in a different way. It is a different mechanism. This part, which is distal convoluted tubule, it reabsorbs the sodium by different mechanisms. And in the end, your collecting tubule reabsorbs the sodium in a different way. So different drugs interfere with the reabsorption of sodium at different parts of the nephrons, so that less sodium is reabsorbed and more sodium appears as urinary sodium and producing the natriuresis and diuresis. So to understand natriuretic drugs, diuretic drug, first we should understand that what are the normal mechanisms along the nephron, normal mechanism of sodium reabsorption, and then we should see how diuretic drug interfere with those mechanisms, right? We'll be talking about that. How different parts of nephrons handle the sodium, and then logically we'll go to how different diuretic or natriuretic drugs interfere with reabsorption of sodium and water. Look here, how many areas are present there on which sodium handling we have to consider. Let's suppose here's a typical nephron. And first of all, I will talk about this particular cell. The cells in this area, let's suppose I will draw this cell into detail, and I'll tell you how this cell is handling the sodium and water. I mean, what is the role of proximal convoluted tubule, right? This should be our first step, role of proximal convoluted tubule. Then the second important point will come, the thick part of ascending limb of loop of Henle. How it is handling with the sodium. This will be our second segment of information, quantum of information. Next quantum of information should be how the distal convoluted tubule is handling the sodium. And in the end, we shall talk about how the collecting tubular cells, right? Collecting tubular cells are handling with the sodium. So at first, I will go into detail of this one, right? Now, let's make one big nephron and see how it is processing water and sodium. This is proximal convoluted tubule, and here it is a cell, proximal convoluted tubular cell. I've just represented here one cell, but actually there are thousands and thousands of cells on all the sides of proximal convoluted tubule, right? And what is here? Yes, please.
Descending limb of
Henle. Then we'll talk about thick part of ascending limb of loop of Henle. And this is collecting tubule. First of all, we have to see how this cell, which is representing which function of proximal convoluted tubule, how it it's working as far as sodium and water is concerned. In second part, we'll talk about this cell. What is this cell? Cell of thick ascending limb of loop finally. This will be our second discussion. Third discussion will be how this part, what is this? This cell, what is this? Distal convoluted tubule. And in the end, we'll see how this particular cell is handling with, that is collecting tubule. Now, let's talk one by one, step by step. First of all, this cell. When fluid is passing nearby, how it handles with the sodium and water. Okay, here is your vascular system, afferent arteriole. Here is glomerular tuft, efferent arteriole, and this is peritubular capillary network. Right? We were talking previously, from here the filtrate was appearing. Let's suppose here filtrate is 100 ml per minute. Glomerular filtration rate, in this particular case, usually it is approximately 120 ml per minute. Now, when this filtered fluid is passing through the proximal convoluted tubule, what really happens to this fluid? Listen carefully. On the luminal side, the cell has two sides. One side is facing to the lumen. We call it, we call luminal side of the epithelial cell. And then, this is the other side of the epithelial cell, and this side is called basolateral side. This side of this proximal convoluted tubular cell is called basolateral side. Actually, what really happens, there must be one cell here also. There should be one more cell here also. I've just enlarged one cell. Actually, there are special proteins which are holding the cell together like this and like this. These proteins which are holding the cells like this, they are acting as a very special type of junctions, special stitching, you can say, unit. And whatever transporter proteins, cells are made of lipid bilayer. This is the luminal face of the cell, and this is the basolateral side of the cell. And cells are attached with each other with proteins on the sides. Now, what really happens? There are different proteins which are present on the luminal side, which are supposed to handle the, listen carefully. There are some proteins which are present on this side. And there are other proteins which are present on this side. Now, it means these proteins cannot come to the basolateral side. The proteins, the transporters or channels which are present on the luminal side, they cannot float to basolateral side. And the proteins and, you can say, different transporters or channels, or you can say these which are planted by the nature on basolateral side, they cannot come to the luminal side. So we have a very basic concept right now. The luminal side of the nephron cells and the basolateral sides of the nephron cells are having different functions. Why? Because proteins which are expressed on the luminal face of the cell are very different. The transporters, channels, or other proteins which are presented or embedded or operative on the luminal side of the nephron cell are very different than the proteins or different channels or transporters or enzymes which are present on basolateral side. Due to this reason, we say luminal side has different specialized performance and basolateral side has different specialized performance. This is the first thing which we should know, that nephrons are made of epithelial cells. Epithelial cells have luminal faces and they are having basolateral sides. Luminal sides are having different type of functions, and basolateral sides of these cells are having different type of functions. Now let's suppose, what are different functions present over here? Okay, let me tell you. One of the very important thing which proximal convoluted tubule has to do is that it has to reabsorb the sodium. Lot of sodium is filtered here, and out of the sodium must go into cell. It means it has to cross the barrier of luminal membrane, because sodium is a charged molecule. It cannot simply dissolve into lipid. So it cannot go by simple diffusion. So it has to be somehow transported in a special way from the luminal side to the intracellular fluid, and from the intracellular fluid this sodium has to go out of the cell by another specialized mechanism. So there should be some special mechanism on luminal side. There should be another special mechanism on basolateral side. And then in this way, filtered sodium should become intracellular sodium, should be transported by the basolateral side to the interstitial fluid, and from the interstitial fluid, it should go back to the blood. So what is really happening with the sodium? The sodium is coming from the blood, becoming the part of the tubular fluid. The luminal cells should take up sodium by some special mechanisms, and this filtered sodium or tubular sodium should become intracellular sodium, right? And then there should be some specialized mechanism on basolateral membrane. We should take the sodium from the cell to the interstitial fluid, and from there the sodium should go back to the body, right? Now another thing. Sodium is very important to be taken back to the body. But along with sodium, many substances are reabsorbed in the proximal convoluted tubule. Along with sodium, many other important substances are reabsorbed in this area, right? I will not go into detail of that physiology, but first of all, I will talk about how sodium reabsorption is coupled with bicarb reabsorption. You know, it's not the only sodium which filters. Sodium filters along bicarb and sodium filters along chloride. It means sodium bicarb filter, sodium chloride filters. So it means sodium has to go back, bicarbonate has to go back to the body, and even chloride has to go back to the body. Now, first of all, sodium reabsorption I will discuss in reference to bicarbonate reabsorption. That when sodium is reabsorbed, along with that, what is reabsorbed? Yes, please? Bicarbonate. Because it is very important. Bicarb is your very important alkali in the blood. And this alkali freely filters. Bicarb freely filters into filtrate. And we cannot afford to lose all the alkali into urine. Why? Because our cells are all the time producing acid. You know, cells produce carbon dioxide and which react with water and become carbonic acid. That is acid. Our cells during the metabolism are machines. Our cells are such biological units which are constantly producing different type of acids. And to keep the acid-base balance, not only we should get rid of the acids out of the body, it's another very important concept that we must retain our alkali. Otherwise, our acid-base balance will be very much disturbed. So, in the proximal convoluted tubule, sodium is reabsorbed in many different ways. One of the ways that reabsorption of sodium is associated with reabsorption of alkali or bicarbonate. Let's go into detail how it really happens. Actually, there's a very special type of transporter here, right? On which side? What phase is this one? Luminal phase, right? Let me make it that this is the luminal phase. On the luminal phase, there's a very special type of transporter protein. And this protein, right, it behaves in a very important way that it can take the sodium from here in. And whenever it takes some sodium here in, it throws one proton out. So what is the function of this protein? It is constantly taking the sodium in, and whenever it takes one sodium in, it will secrete one proton into proximal convoluted tubule, right? It means along the luminal membrane, what it is doing in transporting the sodium and proton into different directions. So we call this protein sodium proton counter transporters. We call these proteins sodium protons counter transporters. But before I really go into further detail, I just remember to introduce you to a very basic concept about the basolateral membrane, right? Then we'll come back to this information. Actually, you see that sodium is very important substance present in filter, and from different part of the nephron it should be reabsorbed. It means that different cells in the nephron should be normally rich in sodium or poor in sodium. Cells should be poor in sodium so that they can suck the sodium, they can pull the sodium, they can take the sodium from the luminal side to intracellular side. So all the nephron cells are poor in sodium. But why they are poor in sodium? Why they kept poor in sodium? Right? Let me explain what is the mechanism. Actually, there is a very, very special enzyme here, or rather not enzyme, I must say a transporter. This is sodium potassium transporter. Such molecules are present only on the these molecules are present only on the basolateral membranes. What these molecules are doing? These molecules are constantly eating up ATP. They are energized by ATP. And whenever they utilize one molecule of ATP, right, they get energized. Every time they throw 3 sodiums out. They capture 3 sodium from intracellular fluid and throw it out. And they capture 2 potassium from the interstitial fluid and throw into cell. So this is what they are doing. They are transporting sodium. And because they are utilizing energy directly, we call them primary transport mechanism of sodium and potassium. And because they are throwing the sodium out and throwing the potassium into cell on the basolateral membrane, right, by the utility of ATP, we simply call them sodium potassium ATPases. These enzymes are called, or transporters are called, sodium potassium ATPases. Now, these sodium potassium ATPases are planted on all the basolateral membranes of the nephron cells. Look, this is sodium potassium ATPase, isn't it? It is present on which wall? Yeah, basolateral. In the same way, here are also sodium potassium ATPases. Again, they are present only on basolateral membrane. But can they float to the luminal side? Answer is no. Again, this cell also has sodium potassium ATPases, and they are present on which side? Basolateral membrane. Even the cells which are present over here, they are also having sodium potassium ATPases, and they are again present on basolateral membrane. From today onward, you must remember what you should remember. You should remember many things, and one of that is that basolateral membranes of the nephron cells are loaded and decorated with what? Sodium potassium ATPases, and they are constantly throwing the sodium out of the cell and bringing the potassium into cells. It means we can say the nephron cells are rich in potassium and nephron cells are poor in sodium. Now we can come to a very basic understanding that if all the nephron cells are poor in sodium, it means they will love to have sodium from luminal side to the intracellular side. They will love to suck the sodium. They will love to pick the sodium from the luminal side to the cell, because the nephron cells are poor in sodium. Why they are poor in sodium? Because sodium potassium ATPases are constantly performing on the basolateral membrane, and they are throwing the sodium out of the cell. So cells become poor in sodium, so they have high tendency to take up the sodium from the luminal side to the cellular side. But the question is there that sodium is a polar substance. It cannot dissolve into luminal lipids, so it cannot by simple diffusion go into these cells. So different cells have different mechanisms. They have evolved different mechanisms on their luminal side to take up the sodium from the tubular fluid to intracellular fluid. Right? Now, there's so many mechanisms which are operating in different parts of the nephron. I'm talking about one of those mechanisms which operates in proximal convoluted tubule. Let's come back. As I told you, sodium potassium ATPases are constantly operating on the basolateral membrane, and they're throwing the sodium out. So this cell becomes poor in sodium. So sodium will love to come into it. But how sodium comes into it? By help of special transporters or by help of special channels. Here what we are concentrating on a very special transporter which can transport sodium from the luminal side to the cellular side, and during this it will always exchange one proton from or hydrogen from the intracellular side to the luminal side. Is that right? So this molecule is called sodium proton counter transporters. Is that right? Now, when sodium comes in, it is throwing the proton out. Now, what happens to this proton? This proton fuses with bicarbonate. This proton fuses with this filtered bicarbonate. When bicarbonate fuses with this proton, both of them react with each other. They convert into a compound which is called H2CO3. What is it? Carbonic acid. It means in the lumen of proximal convoluted tubule, secreted protons are constantly reacted with filtered alkali. Secreted protons are constantly reacting with filtered alkali, bicarb, and they are constantly generating what? Carbonic acid. And then there is a very important enzyme here. Right? Expressed on the luminal membrane. And this enzyme breaks down this particular substance. What is this substance? This enzyme will work on carbonic acid and break down the carbonic acid into water and carbon dioxide. What should be the name of this enzyme? Yeah, carbonic anhydrase. The name of this enzyme should be carbonic anhydrase. And because it is applied on the luminal side, so this carbonic anhydrase is called luminal carbonic anhydrase. So what did we learn after this? That secreted protons and filtered bicarb react with each other in the luminal fluid and make, yes, they make carbonic acid, and then luminal carbonic anhydrase help it to break down to carbon dioxide and water. And carbon dioxide concentration progressively become more in the luminal side. Of course, this will move from high concentration to low concentration, as we say, and carbon dioxide is lipid soluble, so it will very easily slip into cell. So cell will be receiving carbon dioxide from the luminal side. Plus, cells also produce carbon dioxide themselves also. So carbon dioxide is present into this area. Now this carbon dioxide will react with intracellular water. Cells have a lot of water. Even cells can generate water. When they break down the glucose or fatty acids and other. Anyway, so when carbon dioxide is coming here and intracellular water react with carbon dioxide, then both of them are going into H2CO3, carbonic acid. Again, enzyme which is working here is cytoplasmic or intracellular. What is it? Carbonic anhydrase. Now we see there are two carbonic anhydrases. One variety is decorated on the luminal side. Other variety is present in the cytoplasm. So cytosol. So cytosolic carbonic anhydrase help the carbon dioxide and water to fuse into carbonic acid, which breaks down. This carbonic acid break down into proton and what is this? Bicarb. What is this? Bicarb. And this bicarb will go out through a special exchanger which is exchanging the bicarb with chloride. And this bicarb will reach now to interstitial area, and from here when its concentration become high, it will go back to the blood. So what we have done? Meanwhile, the sodium which was taken in by this transporter, that was also by sodium potassium ATPase will go to the interstitial fluid and eventually to the blood. So what did we learn? We learned one thing, that here this mechanism, what it was doing, it has reabsorbed sodium along with the bicarb, but in a very indirect way, right? Now let me put a question to you. Let's suppose if we have a drug or diuretic which can specially disturb this enzyme. We have a drug and this drug can disturb this enzyme. What is this? Carbonic anhydrase. This is the black drug, and this black drug is able to react with carbonic anhydrase and make its function lost. What will happen really? What really happens that carbon dioxide cannot be generated here, or carbon dioxide and water within the cell, can it be fused or not? So when intracellular carbonic anhydrase is reacting with a drug, and this drug will not allow the enzyme to work, then intracellular carbon dioxide and water cannot fuse. It means cell cannot generate its own carbonic acid. It means cell cannot generate its protons. It means cell cannot throw the proton out. If cell cannot throw the proton into luminal fluid, it means if protons are not going out, then this exchanger is not going to work. So the some amount of the sodium which was supposed to reabsorb through this pathway, that will not be reabsorbed. So we applied the drug on these 2 points. We did not allow, so this cell failed to secrete protons. So proton exchange, sodium is not reabsorbed. So you can say some sodium which was supposed to be reabsorbed here, it may eventually appear into urine. So this will produce some degree of natriuresis. But with this natriuresis, the urine which is coming here, with natriuresis, there will be one more problem. What will be the problem? That whatever bicarb is coming here, does this bicarb have proton to react? No. And even if somehow it react, can it go through all this process? No. So what will happen? Number one, some sodium is not being reabsorbed. Number two, that some bicarb, rather a lot of bicarb, is deprived of the protons, and when they are not receiving the protons, these bicarb remain bicarb. They don't go into carbon dioxide. Number one, protons are not there. Number two, this enzyme is not working. So what really happens? Do you think now proximal convoluted tubule will reabsorb the bicarb? No. So bicarb will filter down or track down into what? Into this bicarb will go down. And major site where bicarb is reabsorbed is proximal convoluted tubule. If a lot of bicarb from here is spilling into distal part of the tubular fluid, there is no very effective way to reabsorb such a heavy amount of bicarb. So this bicarb will also appear into urine. So this person will have not only natriuresis, but he will have bicarbonate urea as well, right? It means this person will have some natriuresis, with that some bicarbonate urea, and of course when sodium and bicarb are going over there, they will pull some water with it, and of course there will be what? Diuresis. And there will be what? Diuresis. So there will be natriuresis, there will be bicarbonate uresis, there will be diuresis. And another important thing, this type of drug will make the urine acidic or alkaline? Alkaline. And of course, when you are losing bicarbonate to urine, so your body is deprived of the bicarb, so body will become acidic. So it will produce this type of drug. Number one, it will produce natriuresis. But remember, the sodium which is not reabsorbed here, it may be reabsorbed from some of the sodium which is not reabsorbed here. Out of that sodium which is inappropriately pushed to the distal part of nephron, some of it will be reabsorbed from distal part of the nephron. So natriuresis will be mild or heavy? Mild. Even though the amount of sodium which did not reabsorb here, right, it will be going to the distal part of the nephron, but in distal part of the nephron there are more mechanisms to reabsorb sodium. So out of the sodium which was not reabsorbed here, some sodium will be still reabsorbed, so extra sodium will appear into urine, but in a small amount. So it is a mild natriuretic. So it will be also mild diuretic. Is that right? And this diuretic will produce bicarbonate urea with it. It will produce the urine which is not only having more sodium, it will produce the urine which is not only have excessive bicarb, but this urine will also have extra water. Am I clear to everyone? Is that right? Now, and it will make the urine alkaline, and of course body will become acidic. The drug which is working at this particular point, this drug is called, yes, acetazolamide. What is carbonic anhydrase inhibitors, and this drug is basically, this drug is, what is the name of this drug? Yeah, it is classically acetazolamide. So here we can say acetazolamide primarily work on the proximal convoluted tubule. It work on the luminal and intracellular carbonic anhydrases. When carbonic anhydrases are not working, cell is not providing the protons to be secreted, so in exchange of those protons, sodium cannot, because sodium protons are not there to be exchanged, so sodium proton exchanger does not work, counter transport does not work, so sodium is not absorbed to some extent here, right? So this sodium will go into distal part of nephron, a part of it will be reabsorbed, part of it will appear as extra sodium into urine, which will produce a mild degree of natriuresis. Another phenomenon along with that will be that when protons are not secreted, then filtered bicarb cannot react with that, and bicarb remain as such, and distal part of the nephron cannot reabsorb so much bicarb, so heavy amount of bicarb will appear. When heavy amount of the bicarb will appear there, then there will be not only natriuresis, there will be bicarbonate urea also, and person's urine after acetazolamide administration will become alkaline, and of course with the time body is losing its alkali, so person's blood will become acidic. Am I clear?